Let's talk about a few other phenomena of light. First of all, let's talk about the idea of dispersion. The colors of the rainbow are the same colors as those produced by a prism, and the color spectrum and the order in which they occur is exactly identical. Even though rainbows are associated with 7 colors, the rainbow is a continuous distribution of color according to wavelength. And you can see here that the visible spectrum extends from approximately 760 nanometers wavelength to a little bit below 400 nanometers of wavelength. And that the colors, red is around 700, orange 650, yellow 600, green 525, blue 475, and violet 400. And these colors are not distinct blocks, but a spectrum of color that changes as the wavelength changes. In a perfect situation, with a pure wavelength of light, that is a light ray that has only one wavelength in it, the refraction occurs at both surfaces and bends as shown in the diagram A. However, white light is not perfect. It is not a single wavelength, but it actually contains these various wavelengths. And for the purpose of this demonstration, they're modestly exaggerated, but because there's various wavelengths, the angles of refraction vary slightly based on the wavelength, and thus they are separated into their various colors because of these changes in angles of refraction, which happen twice as it goes into the prism and then comes out. Part of the light falling on this drop of water does exactly the same thing and is refracted in exactly the same way, but it is also internally reflected. So it is reflected and then refracted in such a way that white light going in comes out of the drop of water as a spectrum of color. And this is how the rainbow is formed. And so at the top here, you see that different colors emerge from different directions, and that you have to look at in various ways and in various locations in order to see the various colors. The rainbow arc results from the fact that the line between the observer and any point on the arc must make the correct angle in order to be parallel such that they can see the refracted ray. So the arc is a function of our ability of the observer. And then you can have double rainbows. And I know there's the silly YouTube video about double rainbows, and I'm not going to get into that right now. A rainbow is a combination of reflection and refraction with white light interacting with water droplets. Now, a lens is a type of prism, and there are various types of lenses. There are converging lenses and diverging lenses. And converging lenses cause light to bend toward a single point called the focal point. Light ray 2 doesn't bend because it's on the axis of the lens. It travels straight through the lens and through the focal point. But a converging lens is such that all the parallel rays that enter into the converging lens converge on the one point, F, which is the focal point. And the distance from the center of the lens, which is the axis of the lens, and F is called the focal length. And if we look at this in more detail, a converging lens, as I said, takes parallel light rays and can converge them on a single point that's beyond the lens. The focal point is the point at which those rays are converging, and the length is the distance from the center of the lens to the focal point. The focal length of a converging lens is a positive number because it's on the other side of the source. The power of any lens is the 1 over the focal length, and it's measured in diopters. So the higher the power, the lower the focal length. Now here is a diverging lens. And a diverging lens is a lens that causes light rays to bend away from the axis of the lens. But if you draw lines from the diverging rays, they will coalesce on a point that's on the same side as the approaching light. And this is called the focal point of the diverging lens. And the focal length is from the center to this point, and the focal length of a diverging lens is negative because it's on the same side as the source. So a diverging lens is a lens that causes light rays to bend away from its axis. Thin lenses have the same focal length, but they are on opposite sides. In the case of the converging lens, it has a positive focal length. And because these are called thin lenses, because they don't take into account dispersion or aberrations that can occur with thicker lenses or prisms. The parallel rays entering a converging lens from the right cross at a focal point on the left. Conversely, the parallel rays entering a diverging lens from the right also cross at a focal point on the right. But this is an imaginary situation because the actual rays are heading out and being diverted. So this situation is an imaginary as opposed to real situation. And what do we mean by that? Well, this shows how these various rays can be used to show where the image ends up. So you use 3 rays to define where the image will ultimately occur. And these 3 rays are called the cardinal rays or principal rays. The first is parallel from the object through the lens and then down through the focal point. The second is directly through the center axis of the lens. The third is through the focal point if drawn on the same side, and then into the lens and then parallel after it passes through the lens. And these 3 intersect at one point, and wherever that is, that's where the image is going to be. And that's where the image is formed. And you can see that the image is inverted, and it's sometimes not the same size. It can be smaller or larger depending on how far the object is from the lens. Now, real images like these can be projected. And that's what defines a real image, is it's an image that can be projected. A real image is an image created that can be projected on a screen or on film or on your eye. A real image of a person is projected onto this film on this camera, or since the lens in our eye is a converging lens, it's also projected on the back of our eye on the retina and is seen as real. Now this is the lens formula. 1 over the d0 plus 1 over di is equal to 1 over f. And then the magnification, m, is h of the image, the height of the image divided by the height of the object, which is also equal to a negative, the distance to the image, divided by the distance to the object. So d0 in this formula is the distance to the object, di is the distance to the image, f is the focal length, and m is the magnification. Now if it's a converging lens, f is negative. If it's a diverging lens, f is negative. If it's a converging lens, f is positive. If the magnification is negative, the image is inverted, like in these two examples. If, on the other hand, the magnification is positive, it's upright. So here we have an example of a light bulb placed 0.75 meters from a lens having a focal length of 0.5. It produces a real image on a poster as discussed above. The ray tracings predict the image location and size. Now you can do the math on this one, but we'll have a couple of examples to go through here in just a minute. Now, as I said before, there are various places that you can put your object. Now, in that first example of the girl, the object was placed farther from the lens than the focal length. And it results in an image that is real and inverted, and frequently smaller than the object. Now in this case, they placed the object closer to the lens than the focal length. And the drawing shows what happens. And what you can see here is the actual image is on the same side of the lens as the object, which means that it's a virtual image and not a real image. You can see that it's magnified and that it is farther, it's beyond the focal length, where the actual object is within the focal length. A virtual image is an image that is formed on the same side of the lens as the object, and because of that, it cannot be projected. Now here's a situation with the diverging lens and what happens with the diverging lens. And what you can see is when you draw your principal rays, that you end up, in this case, the flower is the object. You draw your first principal ray, the second principal ray, and the third, and you can draw a third principal ray, but it actually doesn't help you very much. And what you end up with is where those two rays cross, that's where the image is going to be formed. And with this diverging lens, it's inside but on the same side, and so it's a virtual image. It's now reduced and upright. And when it's a virtual image, the DI is negative. And again, remember, when you have a diverging lens, the focal length is negative. So let's finish this section by talking about a couple of problems. The first problem states that a converging lens has a focal length of 3 inches. Find the position, size, and character of an image if a 0.5 inch object is placed 4 inches from the front of the lens. Equation to answer this problem: 1 over d0 plus 1 over di is equal to 1 over f. So 1 over 4 plus 1 over di is equal to 1 over 3. So 1 over di is equal to 1 over 3 is 0.333 minus, that's 0.250, is equal to 0.83, or 1 over 12. So that di is equal to 12. Now we said that the magnification is equal to minus di over d0. In this case, it's going to be 12 divided by 4, or minus 3. And so the object's going to be 12 centimeters. It's going to be real because this is a positive number, and it's going to be inverted because this is a negative number, and 3 times as big. So its size is going to be 1.5 inches because the original was 1.5 inches. The second problem, an object 2 centimeters in height is located 10 centimeters in front of a diverging lens of focal length -6. Find the position, size, and character of this. Okay. Same formula, 1 over d0 plus 1 over di is equal to 1 over f. So 1 over 10 plus 1 over di is equal to 1 over 6, and this is minus. So 1 over di is going to be minus 1 over 6 minus 1 over 10. So di, when you do the math here, equals minus 3.75 centimeters. So it's going to be on the same side. It's going to be an imaginary or virtual image on the same side of the lens as the object. The magnification is minus di over d0, which is going to be minus a minus 3.75 divided by 10, or 0.375. So it's going to be reduced in size. If you take this times 2, the size of the object is going to be 0.75. So it's going to be 0.75 centimeters in height. And it's going to be upright because it's positive.